this book is very well written and it's easily read. So you can, if possible, please buy the book. So although the author is not me, I think this book is pretty well written book. Okay, so this is the power conversion systems, and everybody use the personal computer to simulate the circuit in the main class. So yesterday I already talked about you, and since this course is an NCS based class, so that absolute grading system is applied. So you only get A, B, or F, and there's no C or no D. So this class is what? 꿀 빠는 class. Yeah. Okay. So today I will briefly talk about some fundamentals of the power electronics, and also we simulate a very simple circuit using the power sim. And I think everybody have used the power sim in your previous classes. Okay, so let's discuss about the switching circuit first. So here, what is the average value of this waveform below? Here, the x-axis, the horizon axis is time, and the vertical axis, the unit is the voltage. And the average voltage of this voltage is what? 2.5 volt. And here, you have this kind of pulse waveform. Then what is period of this voltage? So just 1 second, right? And simply assume that for half cycle, you turn on the voltage, so the voltage is 5 volt. And for the rest of the period, you have 0 volt. Then for 1 second, what is the average value? 2.5 volt, right? So it means this voltage and this voltage's average value is the same, but the instantaneous value is different, right? So the switching circuit is mainly you can implement like this. This is a very simple switching circuit, but in fact here, if you turn on the switch S1, then V would be VDC. If we turn off the switch, then V would be what? In fact, that is floating condition. So it's very difficult to define the voltage at this condition. So to make a certain state, in that case, better to have like this diode. So if you turn off the switch and the voltage, this part can be connected to here, so you can ensure the 0 volt. So one thing we can introduce is the dual switch circuit. Here you have two active switches. So when you turn on S1, you can turn off S2. Then V is same as VDC, as like this. When you turn off S1, you can turn on the S2. Then this negative trail is connected to here. So your V is what? 0 volt. So you can simply implement the dual switch circuit as like this. And what about this condition? S1 and S2, both of them are connected. Can you make this state? You don't use this state because turn on, it makes the short circuit and your voltage source would be failure, right? So this is a simple dual switch circuit, but in fact, many kinds of bidirectional converter use this circuit topology. Okay, and let's simply define some switching frequency, duty, and period. Okay, here your period is defined as Ts. Your duty is what? Defined as the ratio between turn on time over the period, right? And frequency is what? 1 over Ts. The inversion of period is the switching frequency. Typically, you can use several kilohertz to several megahertz to implement the switching circuit. Okay, what about the switch implementation? switch implementation. So in our circuit is basically electronic circuit. So you don't use the mechanical switch as like this. So we will use what? A switch in power electronic circuit is implemented with a power semiconductor, such as the transistor. What kind of transistor you have learned? BJT, bipolar junction transistor. And what about MOSFET? And also IGBT. You can also have the thyristor, and diode can be also considered as a switch. Okay. So this figure shows some power semiconductors like that. Here, basically, we use two types of. In fact, we have one more, but let's discuss only silicon and silicon carbide at this time. In fact, you have the GaN, gallium nitride here recently. Okay, typically we have used silicon as the materials for the power semiconductor, and diode and transistors and thyristors. And in early 1960s, they have used the thyristors, but after the transistor technology have been matured, then mostly we use the transistor to implement the switching circuit, because the controller, turn on and turn off controller is much easier than thyristor for the transistor. Here, for transistor, you have several kinds of transistor. First, the bipolar junction transistor. You have learned the BJT in electronic circuit design course in your sophomore classes, right? And you can use NPN and PNP type BJTs. What about MOSFET? We use a lot of MOSFETs for power switching circuits, and also IGBT, insulated gate bipolar transistor. So we use MOSFET and IGBT recently, and we may not use BJT for new designed circuit, because the BJT, the driving technology is difficult, and their efficiency is not as good as MOSFET or IGBT. So very small power or small signal conditioning circuit, you use BJT, but the power electronic circuit, you don't use BJT. Okay? Then for the MOSFET, we have several types of MOSFET. First, N-channel and P-channel. Even in N-channel, the conventional and SFET and CoolMOS, that depends on the structure of MOSFET building. But we don't need to really know about the structure itself. The structure is researched by the engineers whose major is materials, the semiconductor materials. So we are majoring in power electronics. So as long as we know how to drive the switching devices, that's enough. Okay. IGBT is MPT and conventional trench IGBT, low voltage, high speed. Even we have more selections recently, because the semiconductor technologies have been getting advanced. So, okay, let's consider a washer. 세탁기. What kinds of semiconductors? I mean, the washer usually employ three-phase inverter as like this. Let's consider we have a DC voltage source inside the washer. That is a typical, we use a PMSM recently. Then, to implement this switch, then what kinds of component will be used here? Which one? The most popular switch for the inverter application is IGBT. But you can also use MOSFET. But usually, MOSFET is not suitable for the inverter application. But if you implement the converter application with MOSFET, that will be fine, probably. But it also depends on your topology. Okay? And let's move to the silicon carbide. Recently, we have so-called WBG, is wide band gap power semiconductor. Wide band gap. And in fact, we may have a chance to introduce wide band gap power semiconductor later. Then among them, when you use silicon carbide, and also we use gallium nitride. And they are commercialized, although their price is pretty high compared to the silicon-based device. So still, industry use silicon-based device, but they are getting moved to silicon carbide or gallium nitride. Their driving characteristic is pretty different from the silicon-based device. Okay, for silicon carbide devices, the most popular SiC device is the Schottky diode, SiC Schottky diode, and also SiC MOSFET. Many manufacturers have developed SiC BJT and also SiC IGBT, but only SiC MOSFET is not commercialized because of the simple structure and the reliability. So to implement some high efficiency and high power density converter, if you go with silicon carbide MOSFET, then you can easily get the success. Okay. Now what about SiC Schottky diode? In fact, there are a lot of some historical background, but I may introduce it later. Okay, let's see some symbols here. This is the diode. This is what? Thyristor. This is the gate. So thyristor can turn on through the gate, right? Then, do you apply a voltage or current here? Current, right? For the thyristor, you flow the current to the gate. Then you can turn on the anode to cathode. And this is the IGBT. And this IGBT with the diode. Then it looks like BJT. Also, you have this symbol can be considered as a capacitor. So it is a kind of some mixture of MOSFET and BJT. So, do you give the voltage or current here? Voltage, why? Because its driving gate part is similar to the MOSFET. So, you apply a voltage. Okay, when you turn on IGBT, can you flow the current here? No, right? Because this part is what? NPN BJT. So you really cannot flow in reverse direction. So to flow the current from this is what? The emitter to here, then collector, then you should have the diode. Since you have the diode, can you cut off the current here? No, because as long as you get the current like this, even if you turn off the gate, you can flow the current, right? Because this is the diode. Okay, and what about the FET? Basically, FET is also turned by the voltage at the gate. And it includes the body diode. So even if you don't include the diode here, you can flow the negative current here. But usually the performance of the internal body diode is very bad. So if you want turn on, if you want flow current in reverse direction, you can also give a voltage, gate voltage. Since the MOSFET has a channel, through the channel you can flow the current. But still, we can also add a reverse, the anti-parallel diode is like that. So usually we use a silicon carbide Schottky here. A lot of some semiconductor packages. So we can categorize the switching devices as like this. First, uncontrollable device. Uncontrollable device. For the uncontrollable device, turn on and turn off operation are decided by what? External circuit condition. For example, the diode. And controlled turn on and uncontrolled turn off device. For example, thyristor. Controlled turn on means for thyristor, you can turn on the thyristor through the gate signal. But your turn off condition of a thyristor is what? Same with the diode. Right? So you can turn on the thyristor, but you cannot turn off the thyristor. Then, what about controllable device? Both turn on and turn off are adjusted by the gate signal. That is a transistor, right? But even we have a thyristor, some thyristor can be turned off by the gate signal. That is called GTO, gate turn off thyristor. There are some thyristor like that. And BJT and MOSFET and IGBT is like this. Okay. This is the simple symbol of a ideal switch. We can define this terminal, the voltage across this terminal and this terminal as VSW switch. And the current is defined as ISW switch here. So this is a simple condition of ideal switch. Okay, for ideal switch, there is no voltage drop at on state. It means if you turn on the switch, the VSW is 0 volt. And no leakage current at off state. Means if you turn off the switch, then there's no leakage current. You cannot flow any current. And no transient. No transient. What does it mean? When you turn on and turn off your switch, there's no transient. It means that in practice you have the transient, right? But ideal switch doesn't have the transient. Okay. Then here, this is the typical BI characteristic curve, not curve, BI characteristic of the ideal switch. So when you turn off the switch, you don't flow any current, 0 ampere, but you can survive even under infinite voltage. Then when you turn on the switch, then voltage drop is 0. But you can flow infinite current. That is ideal switch. What about the reverse current flowing? We usually don't consider reverse current flowing the capability in switches. So you can actually flow the reverse current, but we don't consider this situation. Then what about in practice? In practice, if you turn on, you have voltage drop. In practice, if you turn off, you have leakage current. In practice, you have very, very significant transient waveforms. Usually, the power electronics system is failured by the transient, usually. And what about the breakdown voltage? Breakdown voltage. Yeah. In practice, you have the voltage rating. In practice, you have the current rating, but usually the current rating is determined by the thermal capacitance. What does it mean? Okay, there are mainly two reasons to make the failure on power semiconductor. The first one is the isolation. The second one is the thermal. What does it mean? Okay. If you have two conductors here and you apply a voltage, then if you increase this voltage very high, then the current can flow through the air, right? In that case, your semiconductor failure, right? Then let's consider this. You have a conductor and you increase the current. In fact, the conductor has the resistance, right? Then, when you flow the current, then the loss is derived as like that. Then your loss is very high. It creates the heat. Because of heat, this conductor can be disconnected. Then your switch is also make a failure, right? So, as long as you can, you can keep the voltage less than rated, and as long as you can manage your thermal, then your switch will not be die. Okay? But it is very difficult. In fact, it's very difficult. Why? Because of the transient. Because of the transient. It's very difficult. 그렇습니다. Okay. Diode is very, very important. Diode is very important. So, if you select diode, a very good diode, then your circuit will be very reliable. But if you select the wrong diode, then your circuit will be easily failure because of the diode reverse recovery. You have known about the reverse recovery, right? Then the reverse recovery is the main reason to destroy your circuit. So diode is a very important component in power electronic circuit. For example, again, we can derive the inverter as like this. And usually you have the diode here. Then if you use very slow diode here, then your circuit is, you can see easily fire because of the diode. Because of diode, even if you turn off the switch, in transient, you make the short condition because of the reverse recovery. What is reverse recovery? Reverse recovery is you flow current like this, right? Then you turn on the switch. For example, this is turned off. You turn on, your reverse recovery make the reverse current. Then this is what? Short circuit. Because of this, you see the switching noise. When you check, when you measure the voltage or current, you see this kinds of switching noise. That is not just a noise. That is a real fluctuation. And it creates what? EMI, electromagnetic interference. Because of this, your circuit make a wrong gate signal. Then your circuit is usually destroyed. This is very difficult. That's why power electronics is difficult. Its theory itself is very simple, but its implementation is pretty headache. Okay, anyway, let's discuss about the diode. It's like that. This terminal is called it anode. This terminal called it cathode. In fact, cathode spells C-A-T-H-O-D-E, but we usually use the symbol K as like that. And the BAK, which is defined as diode forward voltage drop. So when you flow the current, you see the voltage drop. Typically, in the electronic circuit textbook, it was typically what? 0.7 volt, right? And the current that is the diode, the forward current, or you can say anode current. Okay. Since the diode is uncontrollable device, your turn on and turn off is determined by this condition. So if your anode voltage is larger than K, then you can flow the current. And if your IA, the current is less than 0, then it is just a turn off. So this is the typical ideal BI characteristic of a diode. So when you turn on, you can flow infinite current, and there is no voltage drop. When you turn off, you can flow no current, and you can survive until the infinite voltage. But in practice, it's like this. So you have the breakdown voltage. So if your diode voltage is, if you apply too high voltage from here to here, then your diode can be destroyed. Destroyed means what? You flow a lot of reverse current as like this. Okay. Once your diode is break down, then you cannot use the diode, except the Zener diode. The Zener diode, you can use the breakdown, the region, but you don't use Zener diode for the power conversion circuit. BJT. Okay, although we really don't use BJT recently, I will simply review the characteristic of BJT. So let's define the current as like this here. This current is IB. Then there is a relationship between the base current and the collector current. ICE. Right? So according to the base, the beta, you can control the current, the beta and IB, you can control the collector current. So in the electronic course, microelectronics course, it was about 50, 100 or something like that. But in power circuit, it's not that much high. It's, for example, it is like 10 or less than 10, something like that. It means if you control 10 ampere here, you should flow 1 ampere. Like that. For example, if your beta is 10. Then basically, current is a loss. What? I square R. So, if you want to control the IC, you should flow the current. Then this doesn't give any action to real power circuit itself. So that is just a loss. You can consider it as a loss. So the diode, the BJT's efficiency is not very good. Not very good. If your efficiency is bad, then you should have giant heat sink, right? Low efficiency make large thermal. Then your thermal, the heat create switch failure. So to cool down your temperature of the switching device, you should have a large, the very giant heat sink. There. And your collector current is proportional to IB, with the beta. So you can draw the characteristic curve as like this. So this is the current controlled switch, and we don't use at this time. And your BJT cannot flow the reverse current. So to flow the reverse current, you should have the anti-parallel diode as like that. So usually we use the switch pair. And by doing so, you can flow the current in forward and reverse directions. Okay, this is the MOSFET, metal oxide semiconductor field effect transistor. Here, the turn-on condition is like that. You apply the VGS, that is gate to source voltage. If your VGS is larger than a threshold voltage, then you can turn on the current. And if your VGS is less than threshold voltage, you just turn off. But that is a simple just logic. In reality, it's different. If you give higher voltage, then you can, the turn-on characteristic is also different. But too high voltage is create also some bad effect. So in reality, it's a little bit different. Since it only controlled by the voltage, gate voltage, this device can be called it voltage controlled switch. And previously, I told you, if you turn on the gate, you can flow the reverse current. So you have the both directions current is like that. And the current level, the drain current level is also adjusted by VGS. Okay, let's see this example here. And you know that MOSFETs include body diode, right? And the diode also has a forward voltage drop when you flow the current, right? Okay. For the MOSFET, there's two directions. I mean, the two passes when you flow the reverse current. For example, first here, if you turn off the gate, the reverse current can flow through the diode, right? But if you turn on the gate, the reverse current can flow through the channel according to the voltage drop of the VDS. What does it mean? For example, here, your diode voltage drop is, you can just consider that is a fixed value. For example, 1 volt, for example, 1 volt. So that is regardless of your amount of the current. 1 volt drop is, for example, even if you flow the 1 ampere through the body diode, you create 1 volt. You flow 10 ampere through the body diode, you create 1 volt. But in reality, it a little bit increase. But this case is a little bit different. This channel is modeled as a resistor. Assume that that is 1 ohm. Assume that is 1 ohm. And if you flow 1 ampere through here, then the voltage drop of the drain to source is what? 1 volt. If you flow 2 ampere, then the voltage drop is 2 volt. Okay? So, some current range, the voltage drop through the diode can be higher, even less. Okay? So it depends on the current rating, that voltage drop is different. Okay? Let's consider this case here. In fact, this is the MOSFET, called it AU-IRF 2804L. Here AU means automotive grade. IRF is the International Rectifier Company. And VDSS is 40 volt. It means the maximum voltage across the VDS is 40 volt. In this case, your typical operation range of this MOSFET is less than 20 volt, 20 or 30 volt. Although your voltage rating is 40 volt, you cannot use 40 volt device, 40 volt DC link in this case. Your DC link voltage should be much less than the maximum voltage rating. And here, RDS is the drain to source resistance when you turn on the MOSFET. So when you turn on the MOSFET, you have the channel. That is the channel's resistance. Okay. So you can model as like this. This is RDS. Here, your silicon limited current is 270 ampere. Package limited maximum current is 195 ampere. Okay, low voltage but very high current. This device is employed in automotive chassis control system. Chassis like the brake or steering, something like that. That is called the chassis systems. Okay, assume that you turn on the gate and the drain current is 100 ampere. Then what is the voltage drop of the MOSFET in this case? 0.15, right? 0.15 here. Okay. Let's try a simple example. Assume that your RDS is 1 ohm. Your voltage drop of the body diode is 0.7 volt. And obtain the VDS in each case. Okay, case A. The gate is turned on and your IDR, that is current source, IDR is 0.5. That is turned on. Then what would be the VDS? Minus 0.5 volt, right? What about case 2? What about case 2? The gate is turned on and IDR is 1 ampere. Then what is the VDS? 내 수업이 싫어서 나가는 거야. 잘 갔다 와. 자, what's the VDS in this case? Minus 1. Okay. A, B. What about C and D? What about C? Gate is turned off. IDR is 0.5, as like the first case. What is the VDS at this condition? What about case D? What about case D? 이원빈. Okay. Then let's check if the answer is correct. Okay. Let's move to the PSIM. Learn the PSIM software. And okay, for PSIM, okay, here to simulate the circuit with the PSIM model, then first you should have the simulation controller here. So you can bring the simulation controller below. The symbol looks like a clock. Then now the time step is just 10 microsecond and total time is 10 milliseconds. And let's bring the MOSFET here. MOSFET. And you can the previously you have the current source here. You can go to the source and there's voltage and current, and you go to the current and bring the DC source as like this, and you can just simply make a circuit like that. And to control the gate, you should have the on-off switch controller. It looks like a simple triangle, and you can add a voltage source here like this. And let's measure the drain to source voltage as like this. Then go to here, that is VDS1, and you can display it like here, and simply make amplitude to be 1. And previously in the slide, your own resistance was what? 1 ohm, right? And your diode threshold voltage, that is board voltage drop, that is 0.7 volt, right? You can type as like this. Then make DC current to be 0.5 ampere. Then run simulation. Okay. That is the answer of the case A. Minus 0.5. 현지 리더 good job. Okay. Okay. Let's move to IGBT. IGBT here. Here, the symbol of IGBT is here. Collector, emitter, and gate. In BJT, this terminal was base. But now, IGBT, that is the gate. That is the BI characteristics of IGBT here. Unlike the MOSFET, IGBT doesn't have the capability of reverse current flowing. So to flow the current in reverse direction, I told you, you should have the anti-parallel diode like that. So the turn-on condition is similar to the MOSFET. Your VGS, in fact VGE, gate 2 emitter voltage should be larger than a threshold voltage. Then your MOSFET, I mean the IGBT, can be turned on. If your voltage is less than the threshold, the voltage is turned off. I mean the IGBT turned off. So to make a reverse current flowing capability, you should equip anti-parallel diode as like that. So if you find the diode, some diode, I mean the IGBT, some IGBT include the anti-parallel diode, but some IGBT does not, don't have the diode. Okay, then let's see the chapter 1 here. Okay, the lecture slide is offered by the author, the Professor Byung-Jo Che, and it is pretty well made. So I will use the offered lecture slide here. Okay. In fact, the title is a little bit different. In your textbook is Fundamentals of PWM DC to DC Power Conversion, but the lecture note is First with Modulated DC to DC Power Conversion, Circuits, Dynamics, and Control Designs. So this textbook, in fact, this textbook is a part of this book. Okay? So this book includes this textbook. So in fact, this book is suitable for the graduate student, but the earlier section is also okay for the undergraduate. That's why I use this slide. Okay. Let's explain one by one. Let's consider a simple electric bulb application. Electric bulb application. As like this. Here you have a voltage source, and you have a variable resistor, and you have the electric bulb here. And the source is considered as a battery with variable output voltage, whose range is from 18 to 30 volt. So its minimum voltage is 18. Its maximum voltage would be 30 volt. And the load, you should offer 12 volt here. That is your mission in this slide. Then, if you use the conventional resistive solution, then according to the voltage level, your resistance should be also changed, right? Then, let's see some control law. You have the variable resistor Rx. The bulb is modeled as RO. Then, your control law, output voltage VO is what? RO over Rx plus RO times VB. That should be 12 volts, right? And in this case, you can easily calculate the ohming loss at Rx. P loss is what? Input power minus output power. That is consumed by the Rx. So it is easily written as like that. Here, this is a simple series circuit. The current in this loop is the same, right? The current is defined as I/O. So the input power is VB multiply I/O. And the output power is VO multiply I/O. So input minus output is the loss. Does it make sense? Okay, this is just a simple relationship. Then, let's derive the efficiency. So, we can give this assumption here. Let's assume that your battery voltage is 30 volt. And your bulb consumes 60 watt power at 12 volt level. Then VO is 12 volt, and your IO would be what? 60 watt over 12 is 5 ampere. Then in this case, your efficiency is what? Your output power was 60. Your input power was 30 multiply what? 5 is 150. Minus, the input is 30 multiply 5. Output is what? 12 multiply 5. So the loss is 90 watt. Loss is 90 watt. So you supply 150. You only get 60, and 90 is the loss. Then the efficiency is P out over P in. Then P out is 60. Input is 150. Efficiency is just 40%. 40%. So, consequence of poor efficiency. So your heat generation. So, because of this heat, you should have a giant cooling system, heat sink. Then it essentially increases in weight and size. Let's define the term SPDT, single pole double throw switch. Single pole double throw switch. This is a just a symbol of SPDT switch. And this is a practical implementation. So you can use MOSFET or the active switch is like the IGBT, and you can use a passive switch like diode. You can also use active switch here. You can use both active switches. So think pole double throw SPDT switch contains one pole which is always connected to one of the two contacts and the through the two contacts through A and the through P. And SPDT switch is usually implemented using an active switch and diode pair. 이게 DCDC 파워 컨버전이잖아요. 사실은 이 최병조 교수님이 DCDC 컨버터 쪽 많이 하셨어요. 이제 그분들은 이제 그 모스펫 많이 쓰시거든. 근데 이제 인버터 하는 사람들은 IGBT 많이 쓰니까. 근데 여기서 그래서 예제가 사실 모스펫이 많이 나옵니다. 모스펫이. Okay, DCDC power conversion as alternative solution here. Previously, to drive the bulb, you had the resistor, right? But now you have the SPDT switch and LC filter. LC filter. The role of the SPDT switch is to create this kind of switching waveform. So by adjusting the ratio of T on and T off, you can control the average voltage, right? But the voltage Vx include a lot of harmonics, high frequency component. But the harmonics, you don't want harmonics here, right? So to eliminate the harmonics, you use the LC filter. LC filter. Usually, L is worked as a current filter. C is worked as a voltage filter. And you can use LC filter to remove harmonic from Vx. You can still use RC filter. But why don't you use RC filter here? Because of loss, right? LC filter is the second order filter. So it has the resonance. The resonance is sometimes is pretty headache. But even you have the resonance, you use LC filter. Because in ideal case, LC filter is a lossless filter. But RC filter apparently include R. That is a loss component. So to boost up your efficiency, you have LC filter. Then let's assume that you have ideal switches here, ideal L, ideal C. And think about it. You don't have any loss component. You don't have any loss component. Then input and output power is 100%. I mean the ratio of input and output power is 100%. So efficiency could be 100%. But that is ideal case. In reality, what would be the efficiency in this kinds of circuit? Input is 18 to 30 volt and 60 watt output with 12 volt. Then what would be the efficiency? What would be the efficiency in this case? just 생각해 보세요. 90%? 한 93%? 92, 3% 정도. Previously, if you have the resistor, efficiency was just 40%, at best 40%. In this case, efficiency is at least 90%, I guess. Yeah. Now, apparently, you should have this circuit if you consider the long operation time. Then, your input voltage is high, output voltage is low. Buck boost or buck boost? Which one? Buck, right? Buck converter. A simple buck converter. So you can also easily adjust your output voltage by changing the duty cycle. Okay? So, the reason we use the power electronics technology is what? To achieve high efficiency and also low cost. So that is very important technology. And okay, for next 15 weeks, we will in fact learn more practical power test technology than last year. Okay? 자, 수고했어요.